Welcome to Lecture 1 of Chapter 12. I said in the intro video, and if you haven't watched that, go watch that, because I think it frames the chapter fairly well. But I said in that intro video that things are no longer points. They're not just point particles, and up until now, everything has been a point particle. Whether we're talking about a ball, whether we're talking about a pen or pencil, whether we're talking about a brick, a box, everything has been a point up until now. And we represent those points, right, or those bodies as points, so that way we can draw our forces on them, and we can easily, sum up our forces in the x, y, and z direction, right? So, for free body diagrams, these have been super convenient. Everything's been a point. And that describes translational motion. How does something move through space just kind of as a bulk object, right? So with free body diagrams, everything was a point. It didn't matter where the force was actually acting on that box, say. So I could have, kind of replicating a three-dimensional thing, I could have maybe something where I'm pulling on a rope here. I have my weight, which is kind of straight in the center. I have my free body my normal force, and maybe I have some friction, and maybe I also push down on one end here, right? Let's put another force. That pushing down on one end versus the other isn't actually well represented in the free body diagram, right? And having something off axis, having a force off axis is going to start to make things rotate, right? I can easily think of a scenario in which maybe I have a 2x4. And if I have this 2x4, I can apply a force on this end, and I can apply a force on this end, right? And let's say, just to entertain the thought here, that these forces are equal. They're also opposite. One points up, one points down. Is this thing going to move? No, not translationally, but it will rotate. And I think our intuition can inform us of this, right? If I apply a force on one end down and one end up, this thing is going to start to rotate. So having forces applied on things off axis, not exactly perfectly aligned, is going to, as we're going to see, create torques, create rotational forces, basically. It does matter where you place your forces. Up until now, we've said, no, it doesn't. Now we're saying it does. And it's not a revisionist kind of thing. We're taking a very simple problem, a very simple system, and said, okay, this is how it works completely. And I think we've explored it pretty darn well. But now we're saying, okay, let's complicate the system. Let's complicate our theory. Let's complicate our model, right? And now instead of something that's just, constantly going left, right, up, down, let's allow it to curve, right? To bend, to, spin. So that's kind of where I want to leave the concept right now. I want to take just a quick second and remind ourselves of some angular quantities that we're starting to really have in the back of our heads. So reminder that our angular quantities back in Chapter 4, angular quantities, were things like theta, right? Theta was this angular position. And we could get from, let's say x to theta by saying x over r equals my theta, where r was this radius of my my rotational, circle. If I think about the angular velocity. I'm going to be talking about omega, right? Omega here, the little curly w, is our angular velocity. We can say v, our tangential velocity, our linear velocity, divided by r is equal to omega. We could also say that omega is equal to d theta dt. How fast am I going through an angle? Am I changing my angular position? And finally, we can also say that omega is equal to 2 pi over the period. And the period is that capital T, which is a little confusing. But we also have that expression. Finally, we have alpha. Alpha was our angular acceleration. And following the pattern, right, if I take my tangential acceleration, how fast am I speeding up through the circle? This is not centripetal acceleration, right? How fast am I speeding up through my circle? A divided by r is equal to alpha. And alpha, of course, is also then equal to d omega dt. How quickly am I changing my angular velocity? This gave us a couple interesting translations into our kinematics, right? We then could basically replace any linear quantity with our angular quantity and still get a kinematic equation out of it. So our first angular kinematic equation was omega f equals omega I plus alpha delta t. Our second one is delta theta is equal to omega I times delta t plus 1/2 alpha delta t squared. And our third one, right, would be omega f squared equals omega I squared plus 2 alpha delta theta. If you're feeling like we're taking a Greek class at this point, I think that's very understandable. We've kind of moved straight out from our Latin letters and gone straight into our Greek letters. So anywho, these are the angular quantities that we've been using a lot. To frame where we're going, right, we have a couple big questions facing us going forward. We've already kind of tackled how things rotate in some respect, right? The rotational kinematic equations that we came up with in Chapter 4 start to tackle this. But self-rotation is something that we have not yet tackled. So how things spin around an object or around a point is broadly defined. How things spin around themselves, that's something that requires just a little bit more investigation. But the biggest question that we're really trying to tackle in this chapter is not just how, but why, right? And that was a big transitional thought process moving from chapters 2, 3, 4 into 5, 6, 7, 8, which were all forces. We were really trying to tackle the reason why things accelerated or why things moved. In this chapter, we're really trying to tackle that question of why do things rotate. So we have a base level language here to talk through these things in our angular quantities of theta, omega, alpha. When we started talking about in chapter 5, this idea of a force, right, and to try and justify why things accelerated, we really needed to invoke another quantity as well. We needed to start talking about why things resisted acceleration, right? Why things had this thing called inertia, and how could we measure it? In a similar sense, we need to define a similar quantity, this rotational inertia, this moment of inertia. So it acts kind of like a rotational mass in some ways. that's still about a lecture away. But I wanted to set the stage on some of these quantities, on some of the quantities we're going to talk about. The next video is about center of mass and how to calculate it. Generally speaking, we're going to give you very simple systems to calculate the center of mass, or we'll give you the center of mass. But that's for next video. I'll see you then. Thanks for watching.